Yeah.
Yes.
Let me I'll join on my iPad as well.
Okay.
Oh, what did you think about I thought of you immediately when I saw the Nobel.
Oh, you see, that's quite interesting. You see, I think we start with your course. You see, preparing for studying the complex system, and yep. it happened that I've been also interested in climate study, and all of a sudden this happened. You see.
Yes.
Well, my single word response is it's I forgot the single word. It's joke. It's a joke. It's a big joke, right? If you wish, we can elaborate, can explain why I respond so. If you're interested, but that's interesting. You see, the guy or Manabe, Japanese, PhD American for over 60 years. And he got his Nobel Prize. He shared his Nobel Prize with other two. I'm not very familiar with other two, to be honest. And but certainly these other two are more theoretical theoreticians who study complex system dynamics. And so you can see that the world itself is manipulated according to Nobel's will. It's just for the single person, single contribution. It's a mix. Okay.
Yeah.
I use bad words. It's drug trafficking. You see, people care his result because that very person, Manabe, first, I mean, as early as 1967, he came out, he reached some conclusion by calculation, by what is it called? We're talking about that because if you're interested, we can probably spend more time to discuss this issue. You see, his guy first to invoke or to actually do some modeling of our atmosphere. So it's a great idea, I have to say. But so because at that, you see, in the beginning of 1960s, the computer is not very advanced. Probably he did something by hand at the beginning, right? He simply divided the atmosphere into layers, up to 18 at most, according to his paper. 18 layers, not much. I can show you how to do it by hand. Okay. But the result he achieved is of interest for the current consensus, because he generated the non-zero temperature change, namely 2K. If you go to official Nobel committee's news release, it said is coupled CO2 doubling can respond to 2K surface temperature increase. But if you dig into detail, even actually, I'm listening to his talk 4 years ago. He admitted that without what is so-called the feedback and the original change in temperature, according to his modeling, is only 1.3, halved. So there are many details which he didn't tell the audience. And about his contribution, and but by itself, I don't think he's physics. Okay, some other people probably will disagree. I don't think his contribution has anything to do with the basic idea in physics in the first place.
What?
And he's used primarily he used he's very wise. I have a lot. I congratulate him. He's wise to choosing empirical approach by pick up the American atmospherical standards, namely the dependence of the temperature on the altitude, okay, and at the observation. So he's very smart. He based on experimental data, and by just do some little bit variation, and to simplify the atoms, I can probably draw that graph if you wish.
What, do you think it's unfair to invoke feedback in regards to the climate completely?
Yes, I'll talk about that. Yes, that is a key. Can you see? During my past few years, I'm very critical about this idea of feedback. So basically what happens is that you have the, can we just say this atmosphere, probably make sure that can we just go to the solid, which is Earth, the mud, right? The Earth, the surface, and then you got the atmosphere. Well, depending on how serious you are about you about the description, you can either describe the atmosphere as just uniform. See, you know the uniform distribution. So the density, the pressure and temperature are the same everywhere.
All out.
All out. But Newton's gravitational doesn't allow you to do so. Right? So basically, the density will increase. Can you see? Maybe I can make some. This just slightly. I just don't want to draw too realistic, right? And I just probably just highlight that the atmosphere getting thinner and thinner. So eventually they reach to the probably just almost no air. Okay, at a certain stage, the air must be disappear, right? But nowadays, and the argument is made that the density can go as high as stratosphere. Little bit of the perhaps little bit of the atmospherical physics today. Okay, so this is I don't have prepared this talk because I think about this for years. So this is altitude. Okay, this is z in direction in the normally in the kilometers because it's huge. It's called altitude. Altitude. So altitude is just, for example, they have, they say, well, at a certain stage, probably this is 20 is 0, is 10, okay? And about is 20, is 30 or 40 or something. They either go higher, they go higher than that, is 30. And it can go probably goes even go, you go to 100 kilometers, okay? They just continue, the atmosphere behaves, the distribution of air in that way. It's logical, right? Because the heavier, the density is higher, because closer to the surface, and the larger the gravity will be. So that's why that is
sort of exponentially distributed.
So this is mechanics. You see, this distribution is the mechanics. But the key issues is that how can we describe the surface temperature? That is very important. So this is surface, and the surface you can how do you treat the surface in I just mentioned his name. His contribution is called Manabe. So he has another co-workers, but he's the first author. So that is based on his idea in 1967. That is where the breakthrough was made. The number 2K was made. So basically, they think that the surface temperature will change due to the CO2 doubling. So how did he do that? I just go very briefly. He said that this is what experimentally observed. So basically there is if I draw the temperature dependence, can you see this if I draw this one? So the temperature dependence is almost linear. So this temperature will be linear like this one. So in other words, if the temperature is, if the altitude is lower than 20 kilometers, and that would be the case. And above that, well, they argue that the temperature will behave like this, okay, like this. So this is a little bit of background. I think it's good to know because I think it's a good news for the complex system studies that more fund will flow into that area in the name of climate change because the endorsement, because nowadays the Norwegian Nobel Prize Committee have installed this, that is to say, this is definitely true, okay? So therefore, you can see, you're lucky because you can tell your teacher and just trying to getting a little bit closer to the climate keyword.
They actually told us in the lecture. I've never seen my professor so excited.
Oh yes, because ultimately they will benefit from this reward, the Nobel Prize awarding this year.
I think they were particularly keen on not this guy, but the third guy, the physicist.
Yes, that's why. Well, probably you can tell me, or we can discuss this.
Well, I'm not sure. Yeah. The spin glasses guy or something.
Yeah, spin glass, and also that this cause non-equilibrium complex system. Yeah, that's two guys. That probably more, but they are consensus. They all agree that the action should be taken. Urgent action should be taken to minimize to zero CO2. Okay, I mean this consensus. I tell you what, I didn't realize until I actually dived into this pool, and this consensus actually covers quite a lot of scientists. Not necessarily a big cake, by the way. Anyway, to cut the story short, that this work is just say, well, he just used this. This is an experiment. It's called, by the way, this is called the U.S. model standard. This is called the U.S. government standard. The military use this model as well. This measurement, this profile.
What causes the kink? Wouldn't you think it would continue to decay as the density decreases?
Beg your pardon? The temperature?
See here, it's, you know,
yeah, the density, total density will be like this. Density will be like this.
Right, but why is the function of the density non-linear? Like why is why is it not monotonically decreasing?
Density is just that is due to gravity. So basically, if you use a differential, so use I just write the formula here. That's in terms of the density. Yeah, that density exponential is well known. So basically, if the dp, you say, oh, this is not. Oh, good question. Good question. So dp, not dz, dp dz, the gradients are simply equal to null and g. So this is the density. So this is density. Can you see? This is air density. Good question. Our density. And this is gravitational. This is gravitational acceleration. So the gravitational acceleration. Just Newton's law, gravitational.
I see. And sorry, is this one here? This is temperature.
Yep.
And temperature.
This is T. This T dependence on the Z. This is dependence of the how to call it, density. Yes. Yeah. Why so? Okay, that is story. It's non-story. So this first layer is called the troposphere. You know the troposphere. Troposphere is a lowest layer. About the troposphere is called the stratosphere. And there are a lot of terminology on the way.
A lot of spheres, I can imagine.
Yes, the troposphere. So basically, our jet plane probably just can fly that high or that even lower. You see. And why this is linear? So this is well known. Okay, so this slope is constant actually. The slope is alpha. Can you see alpha here? So the slope, the tan alpha is equal to negative 6.4 something. It's constant, in linear. Good question. Why is it behave like this? Because we have used two different. Some people didn't realize that the temperature we are talking about is meaningful only there is a large number of particles. It's called a thermal temperature. So I have to be careful. So this part is probably a little bit higher. And this part is determined by the thermal temperature, thermal pH, sorry. Thermal temperature is different. Yeah, it's different idea, temperature. Because thermal temperature is basically which is a proportion to the density, you see. And why? So the temperature decrease as the density decrease, all right? But why this temperature, this at a stratosphere, the temperature is called a radiation. There's not much particle, very few. Radiation, equivalent temperature. Equivalent temperature. So therefore, there's no, these two temperatures are not the same ideas. And nowadays, because of course, when people measure, this is actually experiment observed. When people measure this temperature, they have changed the instrument at a certain height. For example, this is called the tropo pulse. There's no physical, but there's some people get this thing called tropo pulse. Okay, pulse. It's called a pulse. Trouble pulse. As if there is a border, but it's invisible. So if you use blue or any other satellite, you can use, you can measure temperature. They change the instrument. So this part is radiation equivalent temperature. So this radiation determined temperature is determined by the intensity. This is a basic law. Can you see that?
Mm-hmm.
So this is thermal temperature. So in the thermal temperature would be proportional to the density, but the radiation temperature, this is radiation equivalent temperature were just equal to very close to the density divided by a constant to the power of 1/4. Can you see that?
And is that what causes the kink in the function?
Yes, of course. That would very much depend on the density of this ion. It's called ion. There are some. If you go higher, actual temperature will go even. The temperature even go higher. My point is, or probably something takeaway is that there are two types of temperature here we used. Otherwise, if we just treat this without radiation, and the temperature will be simply decrease. Can you see? The temperature will be decreased without this radiation. This is two types of temperature, okay? And the two types of temperature, and therefore, for ordinary people, without go to detail, they think, well, that is probably the case, okay? But this is not the issue. So basically, to cut the story short, Manabe is what he did is that he just assumed that once the absorption is absorbed by this called CO2, can you see? This is CO2. Once this absorption absorbs that, majority of the radiation will be moved downward, will radiate downward. So I just emphasize that his idea. So these were downward, can you see?
From the stratosphere.
From stratosphere, close to stratosphere, or even lower, I think, because my model is quite different from their idea. And the argument is they start from stratosphere because where is the ozone layer was? Do you remember the ozone layer in the school? Ozone layer is such that it's actually is oxygen. It's just oxygen with two molecules. But he can shielding, they can protect us from the from UV radiation. And the satellite measurement shows that at the top of near the pole or even New Zealand, there is a hole. Okay, it's a hole. Well, it's not the hole, it's just a minimum density of ozone layer. And that is another story. But that story is relevant to the CO2 related warming, global warming. Nowadays, it's just everything is focused on the CO2. Can you see? I just make it large. Can you see CO2 here? So that is the assumption. Although they acknowledge that a small amount of this absorption will go up. Can you see? Where to go? They go to space. Can you see? I just probably exaggerate too much. This they just make their point. So they have a small amount percentage of this radiation will go upward. Okay.
And is this the so-called feedback?
No. Not feedback. So before we talk about feedback, I just make sure we just cut the story short. All right. So what would happen? So basically, in this case, for if the CO2 became 2 times of CO2, it's doubling, right? And the temperature will change. So from this 288 and that will be go to 289.3 Kelvin.
And that's a hypothetical doubling.
No, it's not hypothetical data. It's actually used this assumption. Can you see? This is called the back radiation or downward. It's called the back radiation by the CO2.
But is the CO2 doubling a scenario, or is that already happened empirically?
CO2W is very close to doubling now because according to the measurement, they change from 300 to 400 or something now. So by the end, definitely they were, according to this trend of the CO2, And by the end of this century, yeah, doubling will certainly happen. Yes.
Okay.
Yeah. So so that's why this is good. That's actually the numbers they use. But you can see that the delta t here is very small without a feedback. Can you see? Chemical 0 here. That is 1.3 Kelvin. Okay.
For a double.
For double CO2, yeah. That's according to this assumption. Remember, they have assumption. Can you see? This is upward. Can you use upward? Can you see? Can we use this downward? Can you see? So this is larger. So this is downward radiation by the CO2. Can you see? CO2 radiation. The downward is stronger. So that you say, yeah, go on.
Is that Kelvin measurement, is that in the troposphere or is that in the surface?
Good idea. This is surface temperature.
Okay.
Everything we are carrying the same surface temperature. So this is TS. This is surface temperature, and the surface temperature can either be the surface temperature or the air temperature near the Earth, because it's very close. See, in a few meters, so a few meters above the surface and at equilibrium. And oh, by the way, they are not talking about short term. They are talking about average when you talk about climate, right? So basically, the air near the surface must have the same or closer temperature as with surface. That is their point.
Is it like a price index almost?
Price index?
Is it similar?
I think they have some. You can use a benchmark idea. This is like an index. So basically, that's something I disagree totally. They predetermined that is the case, okay? And this idea comes from the greenhouse effect. They think the greenhouse, if you go to your backyard, you can build a greenhouse, right? But the roof is sealed. Can you see? It's glass. Can you see? So the hot air cannot go outside. So therefore, the only radiation can come into a greenhouse. And that's for the hot air getting hotter and eventually the surface getting hotter. That is a real greenhouse. They use greenhouse as analog. They have used too many analog. Greenhouse is one of them. But they say, oh, well, yes, they say that assumption. For the greenhouse to happen, to work, they have to assume this downward radiation by the CO2 is stronger.
Is the CO2 invoked as the top of the greenhouse?
At the top of greenhouse, what do you mean?
Like what are they proposing forms the top? Like
well, there's no, it's good question. I think you mentioned it. There's no explanation, okay? So if I just do this very simple, much simpler way. So this is a this surface, all right. So these things, according to common sense, that the density of any gas must be obey the same rule. Can you see? So if that is if you have to redraw that a little bit, so this is Z in kilometers, and that is probably the 20 and 40. Yeah, we just simplify that. So this is 0, the ground, the sea level, this is sea level, right? So if any density must obey this law. Can you see? This is how density change. Can you see?
Yeah.
The lower the more condense, right? That's it. But they don't. They are very smart. They say exactly because this idea comes from studying ozone layer. Ozone layer has a very strange distribution. They have very less, but all of a sudden they got the maximum here. So this is ozone layer, right? This is ozone layer. So that is ozone layer is just O3. It's called ozone. Okay, ozone.
Yep. Ozone.
And so nowadays they borrow this idea that they say the CO2 also distributes in similar way. You see? Can you see greenhouse? Can you see? So they say this, the CO2 also decreased in this way. So CO2, can you see? And this is something I found. This just I think is unacceptable. Okay, it is problematical, right? Because you see how can because you can explain why they got a peak for ozone layer, because the ozone layer is generated by CO2. So basically they got oxygen, many oxygen, if you have the UV, you have UV, right? UV radiation, then it becomes CO3. This is oxygen. So this oxygen 3. Can you see? So therefore, because atmosphere will block this UV, so therefore the oxygen down there is this oxygen. Can you see? Oxygen here have no chance to transform into ozone layer. Got it? So they must to form the ozone layer. They need the source, either cosmic or the solar radiation. So that's why I'm not surprised that ozone layer has a peak all of a sudden at the top, okay, at near the in the stratosphere, right? The stratosphere.
But now an empirical finding. Like
it's not. It's experimental observation. That's due to the satellite launched in the early 70s. It's a big deal because now they actually this Montreal, you have Concord, Montreal Concord. Did you know that agreement? It's kind of like Paris, like Tokyo. Yes, the Copenhagen. It looks like that. But in Montreal Concord, that is dealing with ozone layer. They want to stop everybody to release the CFC, chlorofluoride fluoride, something like that. So it's just old-fashioned refrigerator. Use that material as coolant. It's liquid. Yeah, but of course that's what actually they are very successful. So that's why they are confident they can change the world again. They changed the world already. You see, they by stop producing this CFC.
The fridges. Yeah.
Now they want to fix CO2. Now they want to save CO2. But by the way, to cut the story short, so these what they argue is you can see how silly this model is. So they say these will be approximately equal to that, as if there is a imaginable, is imagined how to say, the greenhouse layer. Can you see? Somewhere, not to know, but somewhere, can you see that? That is the argument. And this is a big
CO2.
Yeah, this is of course this is nothing to do with cloud. By the way, nowadays they just mix the story up. Nowadays they are talking about clouds. Can you see? The clouds is something they cannot avoid. Can you see? The clouds is lower. Can you see? The clouds in this area, in this cloud. But to forget about the clouds, what they say is that, well, if you put the whole this greenhouse, they call the greenhouse gas. That's it, greenhouse, including CO2. So CO2 in particular. So they are they acting as a miracle, like an amplifier. I'm talking about I'm talking about the feedback now. Be ready. So basically, what they say is that, of course, the origin of this greenhouse is they admitted that it's due to the originally the non-wave, the infrared radiation from surface. Can you see? That's true, because when surface is getting hot, they will emit a certain amount of they will emit just to keep the temperature balance. Yes. Oh yes. I can draw that. I can use a red color. I can highlight their argument. Okay. They forget about the clouds. They we just focus on their clear sky model. Okay. Let's talk about the clear sky model. So what is happening is there is a downward radiation. Can you see? And there's also a disproportional. There's a little bit upward. Can you see? They acknowledge that. But here is their story. Our Earth is not made by just a solid, but over half of, probably 70% are ocean, water. You see that? So that's their feedback.
How it reflects.
Yeah. So we got lake, we got ocean in particular. So basically, they argue that, well, that would happen if it happened to what would happen to the ocean? Can you see? Water, water in particular. So water. So of course, what would happen to the water? You boil water. When you boil the water and you got the vapor, water vapor, you see? So water vapor just like, so water vapor go up, can you see? And by the way, that is water vapor is also part of the greenhouse, by the way. Actually, is according to the definition, water vapor, because any gas who absorbed the infrared radiation from surface is called greenhouse gas.
Yep.
Make sense now?
Yeah.
So therefore, they say, well, because it's just hypothetically assume this hypothesis, okay, at the most. So this is the upward radiation, CO2 and others, is larger than, is smaller than the downward. So this is downward, can you see? This is downward CO2, greenhouse. So therefore, obviously, the water will be boiled, not necessarily boiled, but eventually, this water, okay, this water, right? This water. Can you just use a good reflector to get that water warm up? Can you? Let's reflect. You can't.
But to call, say, something like compound interest, would you say that that's a misleading use of the term feedback?
The compound interest assumes that there's a surplus every year. That is the deal. That is a business between bank and you. The bank promise you will get some surplus. Okay, they will use surplus. They will pay you. In general, but of course, in terms of energy conservation, this is not energy conservation.
Yes. No.
Got it?
Yes.
It's agreement. It's agreement. Okay. Because for example, the banker probably at the beginning, they just have more money than all the average people, okay? So they just accumulate more money and use the formula of lending and borrowing. And so they can build the more money. That is a different issue. The surplus, the increment, or the dividends.
Yes.
Who provides that dividends?
A priori.
The dividends must be paid by the banker himself at the priori, yes, at the beginning.
Which isn't a reflector.
Oh yes, of course. If you want to be a banker, probably you can say, well, you can borrow money with no interest, okay? And then promise that I will in the long run, 5 years, 10 years, I will give you 20%, whatever. Could be. It could be. It's money. It's monetary. But in terms of energy, you must explain where does the energy come from in the first place. Without that gain, okay, the feedback is just no influence at all. So that is the key idea. See? Without the gain, there is no gain and no feedback.
And it's just an assumption.
It's assumption. It's imagination. So that's why things getting a little bit bizarre now. Of course, I don't try. I'm very critical to other Nobel Prize. And I mentioned that is in the generativity, the gravitational wave, and the Higgs particles. Okay.